So good afternoon, everyone, or late afternoon for some of you. I know some of you are in Europe, so it's a little bit later. Welcome to our CCNP ENCORE class. I apologize this morning if you went to do some labs. Net labs was down this morning. We actually had a short window planned for maintenance this morning for about an hour, hour and a half, and it turned into a much longer maintenance window. We actually had a RAM chip go bad, and we had all kind of little issues with it after that. We ended up corrupting the vCenter, had to reload the vCenter. It was a mess. So just kind of let you know, we had a bit of a day with it. I think we finally got NetLabs back up around 2 o'clock and had it stable at that point. So I did not get to grade any this morning. That was my plan. I was going to grade stuff. I didn't get to. So just be aware that's why there's nothing graded today. I will work on that tomorrow, and knock on wood, the net labs will stay up and we won't have to worry about any more major issues. Any other questions? We actually strive for 99.999% uptime, but that actually is something like 3 minutes of non-planned downtime per year, and that's a pretty high level. And things just happen. Like I said, we had a window plan this morning to do some simple maintenance, and when we rebooted the server decided to scram on us, and we just had a mess. So some days your days don't get to be like you think they're going to be. So we've been talking about OSPF. I do want to very quickly just go over again a repeat of and a stress on what the path selection mechanism is for OSPF. It is the Dijkstra, or shortest path first algorithm. It uses the cost of the links. And the biggest area people get into problems with the OSPF path and the metric is they don't change that auto reference bandwidth. And by default, what happens is 100 gig, a 1 gig, or a 1 gig, 10 gig, even a fast Ethernet, they all appear to be a cost of 1. So you need to change that auto reference cost based upon your speeds in your network. This is especially true if you're running it in any environment with 10 gig, 40 gig, 100 gig links. Because OSPF will see all of those at a certain point. They'll see them all as the exact same speed and therefore the same cost. Be aware, if you start changing the cost on any router in an OSPF area, change it on all of the auto reference cost, change it on all routers in your entire environment. Make them match across the board. If not, you can get some really, really weird routing problems. Okay, so that's the main item I wanted to show you there. Then I want to talk now about summarization of routes and what happens, and one of the reasons why OSPF is so scalable. And that is, inside of the areas, we've talked about type 1, type 2 LSAs. So we've got router LSAs, which are type 1s. We've got type 2 LSA, which are database descriptors. We've got inside of our areas, all of these LSAs that are being brought in by the routers, looked at, and processed in some way, form, or fashion. In between the areas, though, what happens is all the various LSAs inside of your areas are brought together and put out as a single type 3 LSA. So it is actually possible for 4 type 1 LSAs to become a single type 3 LSA that goes outside the area. In this case, it would be area 1, 2, 3, so that what's getting put into area 0 isn't 4 different LSAs going out, but a single LSA where the area border router has pulled all the information about routes and networks inside of the area and then send those out. Now, by default, however, it still sends an update or an information in that layer, that type 3 update. It sends information about every network inside of the area. So there's no what we would call auto summarization between areas. You're still going to know about every single network in the area. It's just instead of having to deal with all of these type 1 LSAs and other types of LSAs inside the area, you just have a single type 3 that leaves the area, and vice versa, that comes back into the area from areas outside. So that's really neat. But what if we want to go even one step further? What if instead of having 3 networks inside being put into that type 3 LSA being sent out, what if we wanted to summarize our internal network so that they only appear as a single network to our outside? That would also help with route flapping. So By default, if we stay with what we had before, if any network inside of this area flaps, there's still going to be a type 3 LSA that gets sent to tell everyone else, hey, that network went down. But if we've got a network like this, let's imagine here, we got 10.1.12, 10.1.13, 10.1.34, 10.1.24. And so by default, what R4 would do is it would take all the information it learns about all of the different networks inside of Area 1. It would combine them into a Type 3 LSA, and it would send that into Area 0. But it's still going to advertise 10.1.12, 10.1.13, 10.31.34, 10.1.24. Still advertise all 4 of those. But what if we could summarize it so that instead of sending out all 4 of those, and also if one of those 4 links go down, we don't want it having to send something over into Area 0 to tell that, because maybe Area 0 doesn't care, or maybe Area 0 is connected to another 15 areas, and you don't want all that information to go through the other 15 areas. Well, you can summarize. And so what you can actually do is a summary route like this. In this case, they decided to do a 10.1.0/18 summary route. If you remember, the way you summarize is you convert all the routes to binary, find all the bits that match, and then that becomes your summary route. If you knew, let's take a crazy example here, but what if you knew that inside of this particular area, so let's say we knew, I'm going to ask a summary question here. So let's imagine that we had, I'm going to pull this here over to my whiteboard. And by the way, we have a new light board we're going to be using. I can't wait to be able to use it. We've got a couple little things we've got issues with that we're working on, but I can't wait to show you all that because I think it's going to be really neat for class. All right, so but imagine what if we had this, but we knew for a fact that right here, okay, everything to this side of Area 1 was sum 10.0.0.0/8. Okay, we could actually do a different summary route. We could actually make a summary route of 10.0.0.0/8, and there would be a single route that would be sent over as a Type 3. Okay, so it'd be a Type 3 LSA that would be sent from R4 into R0, and R0 and all the routers in Area 0 would hold one single route for everything in Area 0, even if there was another 100 routers out here. Now, is that not efficient? Think about how much bandwidth that would save, and also how efficient that is. Now, if you can't remember how to do summarization, just remember you take the individual networks and convert them to binary. By the way, you automatically know that 10.1 matches on all of these, so I wouldn't even bother converting those to binary. You know that, but I would convert 12 to binary, 13 to binary, 24 to binary, and 34 to binary, and then find what matches, and that would be your answer. So let's do 12. So 128, 64, 32, 16, 8, 4. That should have been a 1. Sorry, 8 and 4 is 12. Last time I checked. Okay. So 8, 4, 2, 1, and then 13 would be 1, 1, 0, 1, and 0, 0, 0, 0, and then 24 would be 1, 28, 64, 32, 16, and 8, 0, 0, 0, and then 34 would be 128, 64, 32, 0, 0, 0, 1, 0. And then we'd look here and we'd say, okay, where do we match all the bits? Well, all the bits match right down through here. Okay. And so that's how they get this /18 right here. It's 10.1.0.0/8, 16, 17, 18 /18, and that is your summary route. Does anybody see a problem with this summary route? Can you spot a problem? Let's convert 11 to binary. 128, 64, 32, 16, 8, 4, 2, 1. So that's 11, 8, Oh, no. 0, 1. That's 8, 9, 10. That's 11. Okay. And then 0, 0, 0, 0, 8, 0, 1, 0. You'll notice dot 10 still matches this. Dot 11 still matches it. So you have to be careful here because those would still match. So you need to make sure that when you do a summary, you need to check it on both sides to make sure that these networks would be actually be on this side. If not, you know, if this over here somewhere in another area, let's say this was area 4. Okay, so let's say this is area 4 here for some reason. And there's a network over here that is 10.0, 10.1 dot 10.0/24. You got a problem, because now you've created a summary route that's telling the network that this is actually over here. Now, it may still work because you may have a longer prefix link that comes in over here, but it may not. So you need to be very careful when you're doing summarization. Does that make sense? Everybody kind of understand how you can get in trouble with summarization, and also how efficient summarization can be. That makes sense? Everybody awake?
Yeah.
All right, Brian got a thumbs up from Brian. All right, so here's another example. We've got all these type 1 LSAs. They are being summarized into, instead of 10.16.1 through 10.16 whatever, or 172.16 through whatever, it's 172.16.00/20, and that is what is being advertised. Now, by default, the metric for a summary LSA is the smallest metric associated with the LSA, but you can also set that. We'll show you that in just a minute. But by default, it's the smallest one that you set. In this case, it was a summary address that you did, which is /20. So let's look at this. So here's an example of inter-area metrics. You'll notice here what happens. By default, you look at R3, all the way on R3, area 12 is interjecting 1, 2, and 3 into area 0. So all 3 of those routes are OSPF inter area, not intra, inter, between areas, inter area. We're going to do a summary. We're going to say area 12, range 172.16.00/16, cost 45. And what happens now is, instead of it sending out all 3, it's actually going to summarize it, and on R3, it's going to have a cost of 46 instead of the lowest cost that would have been in there, which would have been a /24 before. So this is a way with the area range command. By the way, this is exactly how you summarize the area range command. You do area, the range you want, the area you want to actually summarize, the range command, your summary address, and then if you don't put anything there, you don't put any costs, it's going to be the lowest cost that it can find inside of that particular range. Otherwise, it's going to be the cost that you set it. Okay. Previously, you'll notice that the cost was just 3, because that was the cost that came in on the actual routes that came through. Here's something else. Don't get confused by this, because you will see this many times. Whenever you do a summarization, you get a route that is called a route to null 0. It's a discard route, and it's designed in case anything comes in that's part of the summary range, but is not actually in existence. Let's imagine, and let's just imagine for a second here that we had this setup, and R2 also had a default route which went out to, let's say, another router inside of this area. If we did a summary address and it had a, let me actually put this in my, I can do this better with a picture. Let me get you a picture and show it to you. Let's imagine we got this network. Go back to the whiteboard. I know my handwriting's atrocious, y'all, but it's I do what I can. So let's imagine Control-C, Control-V. We've got this network, but let's imagine there's also an additional thing going on here. Let's imagine that somewhere off of area 0, there's an area autonomous system border router. So this is, remember, ASBR, which is typically connected to our ISP. So that would be our way out of our main OSPF network. And so let's say R2 has a default route that points up to here. All right. Now we put a summary route of 172.16.0.0/16 into R2. It's now going to advertise that into area 0. Well, let's imagine that R3 sends something to 172.16. Let's see, we got 123.8.10/24. All right. Now I don't know why it's doing it, but it's doing it for some reason. So just work with me here. So it sends it over. What's going to happen? What's R3 going to do with it? Anybody? Remember, once R2 takes OSPF and sends this summary route over, R3 is going to have an OIA route that goes to 172.16.0.0/16, pointing back to R2. So when R3 tries to forward this packet right here, where's it going to go? Anybody? Put it in chat, put it anywhere. Nobody? All right. It should go to R2. Okay. Because let's look. It's got a summary route. First 16 bits bits match. Nothing else matches. That matches. Boom. It's going to send it over. There's no better. Yep. Back to R2. Exactly, Brian. But now what's R2 going to do with it? R2 has that default route, right? So R2 is going to take it and it's going to go, well, by the way, if it didn't have a null 0 route, it would do this. It would say, I don't have a route to the 80 network, but I have a default route. So I'm going to send that up to the ASBR. The ASBR, by the way, is actually part of area 0 right here. So it's got this same route on it. It's then going to take it and go, that's supposed to go back to R2. And then R2 is going to say, that's got to go back up to the ASBR. And then the ASBR is going to go, and we've got ourselves a routing loop. Okay. So this is why anytime you do a summary route, you also end up with a route to null 0 on the router that you do the summary route on, so that if something comes in that is not actually in existence, but is part of the summary, it will get dumped into null 0 instead of going to the default route. That's the entire purpose of that null 0 route. Questions about that? So if you ever wonder what null 0 is for, that's it. You really want to make life bad for somebody? Do a static route to null 0 on a network that they need to use. Not that I've ever done that before. But just to let you know, that's one way you could actually make traffic in a network go. You could actually do a default route to null 0 and the router suddenly starts dropping everything. Don't do that in the real world, by the way. Very bad idea. Okay. That's too open, by the way. It's better to do it to 1 or 2 routes, and then they don't really know what's going on. It's nasty little things you can do to your students. All right. Any questions about summary and about what happens with summaries? All right. Talk about route filtering. Obviously, filtering and summarization, one of the things we can actually do is to do a summarization, do not advertise, and then that will actually prevent the creation of type 3 LSAs for networks in that range. So let's say for some reason, we did not want to advertise the 2 network as part of our type 3 LSAs between one area and another area. You can do an area 12 range command, put in the network you don't want to be advertised and put not advertised. It will then be filtered out. And it will not be sent as any part of an R3 over to R3 as any LSA. It just simply won't go out. You also can do some other other summarization. We can do inbound summarization and we can do outbound summarization. So we have inbound and outbound summarization. excuse me, inbound and outbound filtering. Inbound will keep it from going into the local database, into the routing table. Outbound will keep it from being advertised out. So there's a different way of using these. So here's an example of what's called a prefix list. Now, a prefix list is simply a list that is used to filter your networks. In this case, you see a prefix list that is denying the network 172.16.1.0 and permitting all other networks. Now, what it says is the second sequence number 10 there says permit anything less than or equal to 32. So that would be any network at all that is not 172.16.1.0. So the prefix list, you'll notice, follows a very similar syntax to an access control list. You will then, if you put that on R3, prefix list filter out, that would deny that route, all right, from being able to go into the database, into the RIB. So here's local OSPF filtering. So let's look at this. We receive an LSA from the neighbor. The LSA will try to install it into the local database, but if you've got an inbound distribute list, it will not allow that particular LSA from the neighbor to go into the routing table. Now, that doesn't mean it can't be advertised to another neighbor. The outbound is what blocks the ability for a network to be advertised to another neighbor. The inbound simply keeps it being installed in the local RIB, local router. The RIB, by the way, is the routing information base or the routing table. So here's a distribute list, IP access list standard ACL filter. And by the way, you notice they're just using an ACL as part of this distribute list instead of a prefix list. Deny 172.16.3.0, permit anything else, and then distribute list ACL OSPF filter in. Now you'll notice if we look here at R2, what that's going to do is R2 will not have the 3.0 network listed in its local routing information base, but it did not block 3.0 from going over to R3. So it did this. It was an LSA from a neighbor about 3.0. It went in and hit this inbound distribute list and was not successfully installed in the routing table for R2. However, it was advertised further down the line. So the inbound distribute list only keeps it out of the local RIB. The outbound distribute list will keep it from going to your neighbor. Okay, so that'll keep it from actually going to the neighbor. So this, what would happen here, if there was any other router on the other side of R3, the 172.16.2.0 network would not be allowed to be sent out via OSPF. So it's important you understand those two things and how that's working inside of route filtering. You've got the in and the out filters. And if it's an inbound distribute list, it is not installed into the RIB. If it's an outbound distribute list, it is not advertised to the neighbor. Okay. Questions? No questions? Well, folks, I want to show you a couple things. First off, you'll notice this week we have, you're working on labs up to modules 11. Next week, you'll see there are no labs due until October 25th. So you've actually got a week to catch up on labs next week. You still have chapters to read. You still have chapter exams to take, but you don't have any labs, additional labs next week. So you can work on labs and get caught up, or you can work ahead if you so want to. All right. I want to talk a little bit about BGP, but before we start a discussion of BGP, I want to go back to the concept of, I need to get rid of some of these, obviously, y'all got so many. My whole thing is going to be slower, but I want to go back to the concept of an autonomous system. So when we look at autonomous system, we talk about it's a group of routers under, and man, my handwriting is terrible, control of a single group running a single interior gateway protocol, or a group of interior gateway protocols. Doesn't have to be a single, it can be a group. Okay. Now, so autonomous systems are typically under control of a single entity. They're running a single interior gateway protocol. So you've got, let's say here's an AS, and let's say this is Stanley Community College, and we have an AS. Okay, I'll go ahead and tell you, we run OSPF inside here. All right. Well, we want to connect to an ISP. So we've got a router sitting here, and we connect to an ISP. Quite honestly, if we have this type of connection, we have no need for anything other than a default route. We have one way out. There's absolutely no reason at all to run any routing protocol in this instance between ISP1 and Stanley Community College's external router. Here's where things get interesting. When you put a second router in here and you connect to a second ISP, you now what is called a dual home system. And when this happens, this is where BGP comes into play, because you're going to start running BGP so that you can control how traffic flows to each one of these, and also how it somewhat you can control how it flows back into you. But what you're going to learn, this is an external BGP or an eBGP connection. There are also things called internal BGP connections, so iBGP, which, by the way, one of the things you want to be very careful of, let's imagine that I'm also, for some reason, I got a router in here and I'm running BGP on it also. The place where people destroy their networks is when they accidentally set themselves up to be a transit network, and this ISP starts sending traffic to this ISP through their network as a transit. That will destroy your network, because I can tell you right now, there's over 800,000 IPv4 routes. It's actually closer to 900,000 now, last time I checked. There's over 800,000 IPv4 routes. If you accidentally do this, your routers will have a route table with 8,000 routes in them, and it's going to destroy your routers. That we won't kill them or anything, you just lock them up. They're not going to be able to do anything. They won't have enough processing power to even route packets. Okay. Now, ISPs are designed to be transits, because they put in $1 million routers, and their job is to be a transit between different large ASs. But you do not want to be a transit. This is why I kind of joke that if you ever work at an ISP, there's kind of a BGP king there. They wear a ring, and in order to change anything on the network, you have to kiss the ring for the BGP person to make any changes. BGP is where you can seriously mess up your network in a very quick fashion. I also call BGP, and this is a little bit, I call it the coffee cup protocol. Now, this is something I made up completely, but I want you to realize something. BGP can be very slow sometimes to you make a change, and unless you do a clear IP BGP process and force it to reset, which you really don't ever want to do in the real world unless you just have to, changes can take a while to propagate through a BGP network. So that's why I call it the coffee cup protocol. It is a protocol. You make a change, you go get your cup of coffee, come back, check to see if the change, if anything's happened. It is not one that is fast. Now, it's very stable, but it's not super fast. Have any of you worked with BGP at all in the real world? I have done very simple eBGP, and that is it. That is the only thing I've ever done. So it's very, I don't have a lot of experience with it, I'll be quite honest. So BGP is an exterior gateway protocol. It is a path vector protocol, which makes it more similar to our distance vector protocols than it does our link state protocols. And you'll see why in a little bit. Now, it is scalable, it is flexible, it is very stable, and it is designed to run over TCP. In fact, it uses TCP port 179. That gives you some interesting things about BGP also, we'll talk about here in a minute. So autonomous systems, if they are actually true autonomous systems, they have a number assigned from the IANA, or Internet Assigned Numbers Authority, and it can be any number up to 4 trillion, 294 million, etc. And so they're working on an additional 4 bytes ASN field instead of the 32-bit we had. If you're going to get an AS number, you do have to show a publicly allocated network range that you have. You need to prove that you have multiple connections. So they won't even give you an AS number if you're not connected to at least 2 ISPs. And then you also need to have a need for a unique routing policy. And so it's something that can't be just solved by distribute list or by route filtering or by doing routing manipulation on your end. If you do get one, however, it will allow you to set up BGP. And inside of BGP, there are some things called path attributes. There are 4 different types of path attributes. One is well-known mandatory. That is an attribute that is known in all implementations of BGP must actually implement. Well-known discretionary are well-known and they can or cannot be. Optional transitive is an attribute that is transitive, which means that if you use it, it will actually propagate with the routing prefixes. And then optional non-transit is an optional one that is not transitive, will not go with the actual prefix updates. If it is a well-known, it must be implemented in all BGP implementations. And it also has to be included in every prefix advertisement. So all well-known mandatory are inside of the prefix advertisements that BGP does for a particular network. A well-known discretionary may or may not be included in the prefix advertisement, and it depends upon the vendor's implementation of BGP and some things that you do. Now, as a path vector protocol, the way that BGP prevents loops is it has a thing called a well-known attribute called AS path. And that AS path appends each AS that you go through. Each AS number is added in as a well-known mandatory attribute that is with every prefix that is advertised. So if you see a routing update come around and you see your number on it, actually it's prepended, not appended, prepended, because it goes in front of the other one. But if you look at the information as it comes in, and in that prefix you see your autonomous system number, you're going to drop that. You're going to drop it. You will not accept that particular prefix advertisement because that's a loop. It's coming through you or could be coming through you. So that's a well-known mandatory attribute that you must have in every single prefix. So it's really a simple loop prevention mechanism. It does have the ability to both work with IPv4 and IPv6, so it has the address family ability. So either one of those, we'll talk about multi-protocol BGP in another chapter, but it does have the ability, MP BGP does. BGP does not have its own hello packets to discover neighbors. It is dependent fully upon TCP. Because of this, you can get some interesting things. And that is, for instance, routers don't have to be directly connected to be BGP peers. As long as R2 can get to R4 with TCP, it can create a BGP peering session with those going through R3. Now, it must have some type of route inside of R2 that would let it get to R3 through another protocol. It could be a static route. It could be another interior gateway routing protocol. It cannot be a default route, however. A default route will not allow you to create a BGP peering session across or between 2 non-connected peers. But this is very interesting because it opens up a huge amount of differences between our other routing protocols, okay? The other thing you have to watch out for is you have to make sure there's nothing blocking TCP port 179 between any BGP peers. So make sure there's no firewall blocking it. There's nothing that could block TCP 179. Otherwise, you're not going to form a BGP peering relationship, okay? Here's something else I want to show you that is one of the things that I find super interesting about BGP. To this point, we have discussed protocols that depend upon a very simple thing to put information in the routing table. So let's imagine we've got two routers connected together. Let's imagine this is 10.0.0/30. .2.1/30 here. Okay. Over here is a network it's connected to that is 10.10.10.0/24. All right. 24. And we are going to set up, let's just say for grins, on router 1 here, we are going to set up OSPF. All right. So go into config T, we go router, OSPF, process ID, whatever we make it, okay? Our next item, we're going to then put our network statements in. So what network statement would I put in for R1? And I know there's multiples you could put in, but let's just imagine we're going to actually tell it each one of these networks. What would you put in? Anybody? Earth class. Put it in chat, come off mute. I know y'all know this. You're going to do 10.10.10.0.0.0.255, area 0, right? So we put that in area 0. What's our next one going to be?
10.0.0.0.003.
3, right? .3, 003, because it's 252. And then area 0. Okay. And then on R2, we could only put into our network to advertise 10.0.0.0. So what you have learned to this point is you have learned that in order for a routing protocol to advertise a route, it must have a directly connected interface for you to put a network statement into that routing protocol. BGP is different. BGP, so let's imagine that for some reason I was running, and I know this wouldn't really happen. But let's imagine that this R2 is running BGP with this ISP. Okay, so we're going to have BGP here. You can actually advertise the 10.10.10.0 network with BGP if R2 has learned it from some other protocol, or if R2 has another route to it via static route. So with BGP, networks don't have to be directly connected to be advertised into BGP. This is the only protocol you will study that I know of that you can do this with, okay? To actually do a network statement saying advertise this network, and it will do it, and it's not directly connected. But what it has to do, if you tell it to advertise 10.10.10.0/24 inside of BGP, R2 must have in its route table some way to get to this through another routing protocol or through a static route. It's not recommended you try it with a default route. It won't actually advertise it. It doesn't like to advertise it. I'm not saying you couldn't force it with a connected static or something of that nature, but it does not like to do it through a default route. But if you had a static route that was to 10.10.10.0, or you had an OSPF route to 10.10.10.0, and you told BGP to advertise it out to the ISP, it would do it. But R2 is not directly connected to 10.10.10.0. Okay, so that is to me, that is one of the most interesting facts about BGP. But it makes sense because with ISPs have to be able to advertise routes to other networks so that they're transitive, so that I can get over to Cisco.com and I learn about it because Cisco.com tells its ISP what networks it's part of. And then that ISP, it's not directly connected to Cisco's networks, but it then has to take BGP and advertise that over to other BGP peers, and that gets sent out through the internet. So in order for BGP to work, it has to support this capability.
Yeah, I have one question. Like router 1 and router 2 are in the same autonomous system. Is that correct?
Yes, exactly. They would have to be on the same autonomous system.
Yeah, because there is no valid next hop. Okay, that's good.
This would be an autonomous system here, whatever it be, say 4,000 or whatever, yeah. And then this out here, this would be another autonomous system, so maybe 500 or whatever. Yeah.
Yeah, but they're still directly connected.
Yeah, these right here are directly connected. This would be an eBGP, an external BGP connection.
And the connection between router 1 and router 2 has an underlying routing protocol.
Correct. Yeah, you'd probably be running in here either OSPF or, you could, this is a very simple network. You could probably do static routes on this network, but you wouldn't, you don't have to. You could do OSPF and then you're running, in this case, I did OSPF, but yeah, you'd be running OSPF internal to the autonomous system. And then using BGP, you would take those routes you're learning via OSPF and you would send them out externally to the ISP. And you're going to more than likely, you're going to summarize those routes before you actually send them out to your ISP.
One more example. If you added another router to system 4,000.
Okay, so let's put another router up here.
Yeah, anyway, yeah. Now, it'd be the same thing with we need a full mesh connection.
No, you do not. No, we're not talking about we're not talking about iBGP right now. We're only talking about eBGP.
Okay.
We're taking this autonomous system that's running OSPF, so you would not have to have a full mesh. No.
Okay.
No. This is just showing a typical internal gateway protocol and how it can be sent out via BGP.
And this is going to work just like this.
Yep, just like this.
Right.
Now, this obviously is a bit of a bad example because I'm only connected to one ISP. You're typically going to be connected to two ISPs. There'll be another ISP up here. Ada, do you have a question? Okay. So typically, you like I said, you won't even get an autonomous system number if you're not connected to at least two ISPs. They won't give you one. But it would still work the same. Okay. So unlike TCP, it can form adjacency with routers that are multiple hops away, since using TCP. And a multi-hop session, you will have to have an underlying route in the RIB in order for you to be able to do that. So again, going back to our example up here, or going to our example down here, if R2 is going to have a BGP peering with R4, it would need to know how to get to R4 with either a static route or some type of routing protocol. Okay. And it cannot be a default route. That will be an exam question, I'm about to guarantee it. You'll have an example of a BGP peering session between a non-connected host. It's not working. Why is it not working? And the answer will be because they're trying to use a default route, or the answer will be to fix it, you need to implement a routing protocol or a static route. So iBGP sessions are within an autonomous system. So if you were running BGP inside, eBGP are between autonomous systems. Most of what we're doing in CCNP ENCORE, the questions are all about eBGP. They're not about iBGP, but they do mention iBGP so that you have a basic understanding. It is used typically by, iBGP is used either in very large networks like military, government, those types of things that run their own BGP confederations, or it's used in very large networks such as ISPs so that they can provide scalability. You have to be extremely careful with BGP. I can't stress enough how easy it is to get your network into a huge amount of trouble if you are not careful. Let me see. I'm going to do current BGP routes on the internet. So, oops. Looking at the most recent search here. Oh, I didn't do it right. Let's see. Ah, here it is. Well, the internet's slow today. Where is my? Here it is. So let's look at the routing table here. This is BGP. The number of routes. Let's see. The number of routes, IP routing table across 2024 varies from as low as 880,000 to as high as 920,000 routes at any one time for IPv4. So imagine the size of the router it takes to hold that routing table. So it went as high as 915,000 to then start as low as 880,000. So if you accidentally set your system up to become a transit network, you're done. Your traffic is over. And that is why most places will not let anyone work on BGP unless they're under supervision of someone who already knows it extremely well. It's a hard protocol to learn to use in a real environment, simply because in our environment, like here at Stanley, we set it up, we leave it, we don't mess with it. The only place you do a great deal of configuration and changes to it is if you're working in an ISP environment. Okay. But the great news is it is scalable. I mean, think about it. A routing protocol that can handle 780,000 to 925,000 routing table entries. It's also why it's a coffee cup protocol. When you're dealing with that many networks and that many prefixes, you can't flap. You can't let one network going down make you change the entire routing table immediately. It has to have a slower pace. Otherwise, the routers would be impossible for them to keep up with what's going on. Okay. So eBGP is the core component of what we do on the internet. It's how our networks connect to the ISPs. iBGP allows what's called multi-hop sessions, whereas eBGP only allows the TTL to be set to 1. Okay. So technically, for this type of thing to take place, this BGP peering, this can only occur in an iBGP environment, because eBGP will not allow a hop count of more than 1. So this type of peering cannot even occur in an eBGP connection. The advertising router modifies the BGP next hop address to be the IP source of the connection. It prepends the AS number so that well-known mandatory attribute of AS path has to be part of the prefix. And then each router that gets that looks at the AS path variable and makes sure it doesn't contain its ASN or its autonomous system number. If it does, it discards it because it doesn't meet the network. By the way, if you know what NLRI is, it's network layer reachability information. It fails it because it fails the path, the AS path loop check, prevention check. We're going to stop after this, but these are the 3 main types of BGP packets, and they are open, update, notification, and keep alive, or I call them OINK. The way to remember BGP is think of OINK, O-U-N-K, open, update, notification, keep alive. The open sets up and establishes our BGP adjacency. Updates, advertise, update or withdraw routes. The notifications are typically used for some type of error connection, and then a keep alive is used to make sure the neighbor is still there. So those are your 4 types of BGP packets. I do want to just real quickly go through this, and then we'll stop for the day. But here's how 2 different routers form an eBGP. Well, really, it's actually how they form any BGP section, but in this case, it's an eBGP. They start in the idle. They then, by using the open, they'll actually do an open or do a connect. Then they'll do an open and send the source IP and the remote AS saying, okay, hey, remote AS, let's form a full BGP connection. The remote will then send the information back, open sent, saying, I saw this. There'll be an open confirm. Then there'll be a keep alive. And once this is gone, you then will have an established session. And once it's established, by the way, when you see BGP is established, that is a good thing. When that happens, they start sending their BGP tables to one another. If any of these fail, one of the first things I'm going to look at is, do I have the ability for TCP port 179 to go between these two? Do I have TCP connectivity between these two? We're also going to learn with eBGP that you manually set who your neighbors are. So you say, my neighbor is this IP address at this autonomous system number. And then when you send these opens, they compare that to what's been set in the routing tables. Or not in routing tables, in the configuration, so that it's actually able to see what its neighbors are. All right. So we're going to stop right there, right before basic BGP configuration. Are there any questions? Remember, again, we will have class next week on Wednesday. We do not have any additional labs due next week, so it's a good week to catch up. I will catch up on grading tomorrow, and then we'll go from there, everybody. Thank you all for your hard work. I
Thank
do
you so
greatly
much.
appreciate it. I hope everyone's doing well. We finally got our department just about well, which is a good thing. That cold I had has just absolutely ravaged our department.
I like to ask one question after class.
Okay. I'm gonna stop the recording. I'm gonna walk out of the office for just a second, Clay, and I'll be right back.